Hi guys, so today we're going to be starting on proofs, specifically introducing postulates and paragraph proofs. Okay, so let's get started with some definitions. Okay? A postulate or axiom is a statement that is accepted as true. The reason why is because at the basis of any argument or belief system, we're just going to have to hold some things as true whether or not we can necessarily prove them, right? And so that's where our postulates and our axioms come in terms of geometry, okay? Throughout this lesson, as well as the chapter and the book, it's going to list postulates or axioms, as well as theorems. Some of them have names and some of them do not. What the book has done is it's tried to give names to them by putting numbers in front of them, like 2.1 or 2.2. However, they don't actually have any meaning beyond this book. They don't really have any meaning in terms of geometry. If you went to another geometry teacher and you talked about postulate 2.1, they will have no idea what you're talking about. So as a result, if you're going to refer to these postulates, axioms, or theorems, you either call them by its actual name, if it has one, or you're just going to have to write out the postulate or axiom. If on your homework you write something like 2.1, 2.2, or if you write that on your test, it will not be considered correct because it has no real meaning in the world of geometry. Okay, you're going to have to write out that postulate or axiom. Okay. So we're going to start off with our first two postulates or axioms here. The first one is that through any 2 points, there is exactly one line, right? So for example, you can pick this point here and this point here, and you can see it's connected with one line, okay? Even if you pick something like here and here, even though there isn't a visible line right now connecting it through this page, we can imagine a line going through here, okay? And that goes with anywhere in space, right? Whether we're talking about the tip of your nose to one of your toes, there's an invisible line connecting it, whether or not you actually see it, okay? And then the other postulate here is that through any 3 points, not on the same line, so not collinear, there is exactly one plane, one flat surface that connects all 3 of these points. Okay? And so with that, we're going to get started with example 1. Okay? So here with example 1, it says each of 5 computers need to be connected to every other computer. How many connections need to be made? Okay? So first thing we know is that there are 5 computers, and so each one has to be connected to all 4 others. Okay? And so how we went about solving it is that we drew it. Okay, so each point here represents a different computer, right? So 1, 2, 3, 4, 5 computers. And then all we did is we drew a line connecting each one. So connecting A and B, A and C, A and D, A and E, right? And then B, it was already connected to A, so then we add in the BE, BD, and BC, right? With C, right, we already have a connection with AC and CB, so we just need to add the other ones, okay? And as we keep connecting them, what we realize is that, so the connection between computer A and computer B is the same, so we don't have to draw it again. So for these 5 points, we count them, 10 segments are drawn, okay? And each of these segments represent a connection, and so there's 10 connections in all, right? So now we're going to work on CYP1, which is determine the number of segments that can connect 4 points, and once you're done with that, you're going to come and check it. Okay, the answer you should have gotten is 6. Here is a diagram showing them, and then you just count it, all your lines that you drew. Okay. Okay. Next is using postulates. So before we get to example 2 in our book, we have a couple more postulates. Again, you cannot just write the number of it. It has no meaning. Okay, you have to write out the whole postulate. Okay. So 2.3, a line contains at least 2 points. This one is a plane contains at least 3 points, not on the same line, right? Which is why we name a line using 2 points and we name a plane using 3 points. Okay. If 2 points lie in a plane, then the entire lane containing those points lies in that plane. Okay, so if we have 2 points on a plane, or on a surface, the line that has those 2 points is going to be on that plane. Basically, that's what this third one means. If two lines intersect, their intersection is exactly at a point, right? So if you think about, oh, I have two lines, however they intersect, whether it's flat or whatever, where they touch is considered 1 point, okay? The next one is if two planes intersect, their intersection is a line, right? So one way to think about it is like if I have this surface here, this paper, this is a plane, and I have another plane like this, where it touches is this line, right? And so that's what's demonstrating if two planes intersect, their intersection is a line. Okay. So next with example 2, we're going to determine whether each statement is always, sometimes, or never true, and we're going to explain. Okay. So the first one says, if points A, B, and C lie in plane M, then they are collinear. Okay. Actually, I think I'm going to do it on the paper so that way I can draw for you all the examples. Okay, so if points A, B, and C lie in plane M, then they are collinear. This is sometimes. Okay, here let me explain. For example, if I have here plane M, okay, I can have A, B, and C here, and here they are collinear. Okay. I can also see another possibility, right, where if this is plane M, I can have A, can have B here, and I can have C here, but here, as you can see, A, B, and C do not lie on the same line, which is why A is sometimes. It can, but it can also not. Okay. B is saying there is exactly one plane that contains non-collinear points P, Q, and R, and that is always, okay? And the reason why is because of our postulate, okay? Our postulate here, again, you can't write the number means nothing, but we have a postulate that tells us through any 3 points not on the same line, there is exactly one plane that contains them. And so the reason that is always is because of that postulate. Okay. In C, it says there are at least 2 lines through points M and N. That is never true. Right? And the reason why is because of the postulate that tells us that through any 2 points, there is exactly one line. Not 2 lines, not 3 lines, not 4 lines. There is only one line. So that is example 2. You're going to work on check your progress 2 and then come and check your answer once you're done. Number 2 is always true no matter how you imagine it. If 2 lines are on the same plane and they're intersecting, that's the definition of coplanar, that they're going to lie in the same plane, right, wherever they intersect. So the next and last example is example 3, which is paragraph proof. Okay? So let's look at the book to see how it talks about proofs and paragraph proofs in general. Okay? So in the part about paragraph proofs, so undefined terms, we talked about that in our first lessons. Those are things like points, lines, planes. Undefined terms, their definitions, postulates, and algebraic properties of equality are used to prove that other statements or conjectures are true. Okay? Once a statement or conjecture has been shown to be true, we call that a theorem. Okay? And after that, it can be used to justify other statements are true. Okay? So that's the difference between postulates and axioms compared to theorems. For postulates and axioms, we assume that they are true. We take that they are true. We do not have to prove that they are true. However, for theorems, Theorems are things that we've proven to be true, often using axioms and postulates. Okay. So here, you're going to study and use various methods to verify or prove statements and conjectures in geometry. And a proof is a logical argument in which each statement you make is supported by a statement that is accepted as true. Okay. So how a proof works is that we use things like this, undefined terms, definitions, postulates, algebraic properties of equalities, as well as theorems, in our proof to show this logical argument. One type of proof that we're going to use is known as a paragraph proof. It's also known as an informal proof. In this type of proof, the reason why it's called that is because you're writing a paragraph to explain why a conjecture for a given situation is true. Okay? 5 parts of a good proof. You should state what you're trying to prove. So either whether it's a theorem you're trying to prove or a conjecture you're trying to prove, you need to state that. The second part is you should list the given information, because that is often what you're going to build your proof off of. The third thing is, if possible, you're going to draw a diagram to illustrate the given information. Okay. That will also help you to organize what information you have or as you're adding it. 4 is state what is to be proved. So that's kind of similar to 1. And then the 5th one is you're going to develop a system of deductive reasoning. So that takes us to example 3. Okay. So given that M is the midpoint of segment PQ, we are writing a paragraph proof to show that PM is congruent to MQ. Right? So M here is the midpoint of this. We are proving that this section here is congruent to this section here. So note that in the paragraph proof now we're writing given. We're told that M is the midpoint of PQ. What are we trying to prove? That these 2 segments are congruent. Okay? And so here's the proof. We're writing it out. Okay? So basically it's kind of like whatever our reasoning is or logic is, we're just writing out in paragraph form, in sentences. Okay? So from the definition of midpoint of a segment, right, PM is equal to MQ. Right? The length of PM is equal to the length of MQ. Okay? The reason why we're starting here is because that was what was given. If we know that M is the midpoint, let's start. What do we know based on that information? Well, we know the definition of midpoint, and therefore PM is equal to MQ. Okay? And so what this means then is that segment PM and MQ have the same measure, right? That was what was shown in the sentence before that. Okay? Then, by the definition of congruence, if 2 segments have the same measure, then they are congruent, right? And that's based off of what sentence 2 said, where they have the same measure. Okay, so now we're saying, oh, by definition of congruence, they're congruent. And therefore, we can then say segment PM is congruent to segment MQ, and that is based off of sentence 3. Okay? So what you can see here from our proof is that our first sentence is often based off of what our given is and what we know based on our given, right? And that every subsequent sentence builds off of what happened before, right? And so now we're going to try it out with Check Your Progress 3. Once you have what you think is your paragraph proof is entered in, come back and check your answer. Great. You should have something along this line. I just wrote what was given, what was proved, and then based off of that, I drew a picture. And this is my paragraph proof. It is given that segment AC is congruent to segment CB, meaning that the length of AC should equal the length of CB from the definition of congruent statements. It's also given that C is between A and B, meaning all 3 points here are collinear. And as a result, by the definition of midpoint, right, C is the midpoint of segment AB. And then so from here, Our book teaches us about the midpoint theorem. Okay, so whenever you want to talk about that, this is the midpoint theorem. That is its official name. So if M is the midpoint of a line segment, like segment AB, then segment AM is congruent to segment MB. So whenever you want to refer to this in your proof, you would call it your midpoint theorem. Okay? That's it for today. Have a great rest of the day. Bye, guys.